Lithium-ion batteries hit thermal runaway at 360 degrees Fahrenheit. Flames reach 1,100 degrees Fahrenheit in minutes. One cell ignites the next in under 60 seconds. Tesla's 2026 aluminum-ion testing reveals something different. Cells survived 480 to 570 degrees Fahrenheit without combusting. Punctured, crushed, overheated, they shut down instead of burning. The trade-off? Model 2 delivers 220 to 250 miles instead of 300. Is losing 50 to 80 miles worth eliminating garage fire anxiety completely? Most people think they understand battery fires, but there's a fundamental difference that changes everything. When gasoline catches fire, you spray foam or water, cut off the oxygen, and it's done. Lithium-ion batteries don't work that way. At 360 degrees Fahrenheit, the polymer separator inside each cell begins melting. Push it to 390 degrees, and the cathode materials start releasing oxygen internally. This is the critical point. The fire doesn't need outside air to sustain itself. The battery is generating its own oxygen, feeding its own combustion from within. What happens next is a cascade failure that fire departments train for but still struggle to contain. One cell reaches thermal runaway. Internal temperature spikes to 1,100 degrees. That heat transfers to the neighboring cell in under 60 seconds. Then the next cell ignites. Module by module, the entire pack transforms into a self-sustaining furnace. Fire crews arrive with hoses and spray thousands of gallons of water. The flames die down. Everyone breathes easier. Then 6 hours later, the fire reignites because the electrochemical reactions are still occurring deep inside the pack. Some EV fires have consumed more than 30,000 gallons of water before full suppression. Now consider where you charge your vehicle. If you're like 80% of American EV owners, it's in an attached garage less than 20 feet from your living space. You plug in at night, go to bed, and trust that the thermal management systems will handle everything. Most nights they do, but you're sleeping beside a battery pack storing energy equivalent to hundreds of pounds of TNT. It's stable under normal conditions, but the failure mode is catastrophic. This is the quiet anxiety the industry doesn't discuss openly, the risk that insurance actuaries price into every policy, but marketing departments carefully avoid mentioning. Tesla's 2026 aluminum-ion testing results flip this entire risk equation. When aluminum contacts oxygen, it immediately forms aluminum oxide, a molecular layer just nanometers thick that prevents further oxidation. There's no internal oxygen generation, no self-sustaining combustion, no thermal runaway cascade. Lab testing pushed these cells beyond 500 degrees Fahrenheit without ignition. Engineers then moved to abuse testing, deliberately crushing cells, puncturing them with metal rods, and bending them past structural failure points. In every scenario, the cells responded by shutting down electrically. Voltage dropped to zero, but no flames appeared. No smoke, no heat propagation to neighboring cells. Compare this to lithium-ion behavior under the same conditions. A single puncture from road debris can create an internal short circuit. The damage might seem minor initially. You drive home, park, plug in. Hours later, that microscopic short circuit generates localized heating. One cell enters thermal runaway. The vehicle is now a ticking timer, and you're asleep upstairs. What makes Tesla's silence on this topic so telling is the strategic calculation behind it. No press releases, no Elon Musk tweets proclaiming fireproof batteries. Why? Because openly discussing fire risk reminds customers that current lithium-ion technology can burn in the first place. The entire industry operates under this unspoken agreement. Everyone prices fire risk into their engineering models, but nobody markets it as a primary concern because doing so would undermine consumer confidence in EVs generally. This creates an interesting dynamic for aluminum-ion deployment. Tesla can introduce the technology quietly, positioning it as a cost optimization rather than a safety revolution. Model 2 launches with 220 to 250 miles of range, targeting urban commuters who rarely exceed 70 miles daily. The lower range gets attributed to market positioning rather than chemistry limitations. Meanwhile, the fire risk elimination, the actual selling point, becomes an implicit benefit that insurance companies notice even if marketing materials stay quiet. Let's address the range question with actual usage data. The average American drives 37 miles per day. Heavy commuters might hit 70 miles. Long-distance road trips, where 300 miles versus 220 miles creates real inconvenience, represent roughly 3 to 5 events per year for typical drivers. For daily use, a vehicle offering 220 miles is functionally identical to one offering 300 miles because you're charging overnight regardless. The difference exists in spreadsheets, not in lived experience. What does change dramatically is weight distribution. A Model 3 lithium-ion pack weighs approximately 1,000 pounds, with up to 200 pounds dedicated to protective structures, fire barriers, liquid cooling channels, reinforced casings designed to contain thermal runaway events. Aluminum-ion chemistry eliminates the need for aggressive containment. Remove 150 pounds of passive safety equipment, and the vehicle becomes more efficient per mile, responds better under braking, and handles more precisely. Fast charging behavior reveals another hidden advantage. Lithium-ion cells degrade measurably under repeated DC fast charging, particularly above 80% state of charge. High current generates heat. Heat accelerates dendrite formation inside the cell, eventually creating internal short circuits. Aluminum-ion cells demonstrate significantly reduced dendrite formation because the aluminum anode is inherently more stable. You can fast charge aggressively for years without the same degradation penalty. Run the numbers over a 5-year ownership period with twice weekly fast charging. A lithium-ion pack might retain 80 to 85% of original capacity. An aluminum-ion pack could retain 90 to 92%. You started with less range, but you ended with better range retention. This matters enormously for used vehicle values and customer satisfaction in years 3 through 7 of ownership. Beyond personal vehicles, aluminum-ion deployment in stationary storage makes even more strategic sense. Powerwall units sit inside residential garages, often sharing walls with living spaces. Megapack installations occupy grid facilities near critical infrastructure. A thermal runaway event in a Powerwall destroys the homeowner's property and creates legal exposure for Tesla. A megapack fire at a grid storage facility could disable emergency power during peak demand, affecting hospitals and municipal systems. Aluminum-ion batteries eliminate these catastrophic scenarios entirely. For stationary storage, energy density becomes almost irrelevant because the battery isn't moving. What matters is predictable performance over 15 to 20 years without catastrophic failure modes. Add in aluminum's material cost advantage, roughly 30 to 40% cheaper than lithium, and the economics become compelling. Lower raw material costs translate directly into reduced Powerwall pricing while simultaneously improving safety margins. Tesla's deployment strategy reveals sophisticated long-term thinking. Launch aluminum-ion in lower margin, safety-critical applications first. Model 2 and Powerwall serve as real-world proving grounds. Build production expertise, demonstrate reliability at scale, then migrate the technology upward into mid-range Model 3 and Model Y variants as energy density improves. By 2028 to 2030, aluminum-ion could power half of Tesla's fleet without anyone noticing the transition because it happened gradually across product tiers. This approach carries minimal risk while creating maximum strategic optionality. If aluminum-ion performs as testing suggests, Tesla gains a massive differentiation advantage. If unexpected issues emerge, the exposure is limited to lower-tier products. The technology develops in public view without overpromising or under-delivering. The broader market implications extend beyond Tesla's product line. If aluminum-ion eliminates fire risk while maintaining adequate performance for 70% of use cases, how do legacy automakers respond? General Motors, Ford, Volkswagen are all locked into lithium-ion supply chains with multi-billion-dollar commitments. Switching chemistries requires retooling factories and renegotiating supplier contracts. Meanwhile, Tesla moves first and resets consumer expectations for what safe means in EV design. Insurance companies will notice before consumers do. Actuarial models price fire risk into every EV policy. When aluminum-ion vehicles show zero thermal events after 3 years and 500,000 units in service, premium structures will shift. Tesla owners with aluminum-ion packs could see 10 to 15% lower insurance costs. That pricing difference becomes a marketing point without Tesla ever mentioning fire risk directly. Battery anxiety has shifted over the past 15 years. In 2010, people worried about running out of charge mid-trip. By 2020, concerns centered on charging infrastructure. Now approaching 2026, the anxiety has become existential. What happens when something goes wrong? Every viral video of an EV fire reinforces psychological barriers to adoption. Statistics show EVs catch fire less frequently than gasoline vehicles. But human psychology doesn't process statistical risk rationally. We remember dramatic failures more vividly than accumulated safety data. Aluminum-ion attacks this perception problem at its root by removing the most dramatic failure mode entirely. A battery that shuts down instead of catching fire doesn't generate viral videos or fearful headlines. It just stops working, becomes a warranty claim, gets replaced. Boring is the point. Boring is what mass adoption requires. So here's the real question for 2026. Does maximum range still matter when the alternative is zero fire risk? For daily commuters driving 40 miles round trip, is an extra 80 miles of theoretical range worth the psychological weight of thermal runaway anxiety? Comment below. Would you trade 50 to 80 miles of range for a battery that can't catch fire? What matters more, maximum range or eliminating garage fire anxiety? Here's what the 2026 aluminum-ion testing actually proves. Tesla didn't just improve battery safety, they eliminated the catastrophic failure mode that's haunted EV adoption for 15 years. Lithium-ion fires reach 1,100 degrees and reignite for days. Aluminum-ion cells shut down at 500 degrees without flames. That's not incremental improvement, that's a different category of risk. So back to our opening question, would you trade 50 to 80 miles of range for zero burn risk? For the average driver doing 37 miles daily, those extra miles only matter on paper. But fire anxiety? That's real every time you charge overnight in your garage. Model 2 launches with this chemistry in 2026. Powerwall units follow immediately. By 2028, mid-range Model 3 and Y variants adopt aluminum-ion. By 2030, half of Tesla's fleet could run on batteries that can't catch fire while competitors stay locked into lithium-ion supply chains. The company that solves safety first wins the mass market second. What happens when your insurance drops 15% because your battery chemistry can't burn? Drop your prediction in the comments below. If this breakdown gave you clarity on where battery technology is actually headed, hit that like button. Subscribe to Tesla Zone for analysis that connects engineering data to real-world impact. Turn on notifications so you catch our next deep dive. The battery revolution isn't about more range anymore. It's about trust, and trust just became measurable. 8 years of doubt ends now. The 2026 Tesla Semi just dropped, and Elon Musk says you won't even recognize it compared to 2025. Battery switch from LFP to 4680 cuts weight and costs 40%. Drag drops from 0.36 to 0.33, boosting efficiency 8%. Production jumps to 200 units daily at GigaSemi. Add FSD capability, megawatt charging, lighter chassis, redesigned aerodynamics. 8 upgrades that leave Peterbilt and Volvo scrambling. But here's what nobody's asking. If Tesla could build this in 2026, why did they let the industry burn cash on inferior tech for nearly a decade? The truth starts with batteries, and it's more calculated than anyone realizes. Since 2017, every Tesla Semi used LFP battery chemistry. The choice made sense. Lower costs, excellent safety, stable performance in cold weather. But LFP cells hide a brutal trade-off that Tesla managed in silence for 8 years. Energy density. LFP packs significantly less energy per kilogram. To achieve 500-mile range, Tesla installed a massive 900 kilowatt-hour pack requiring thousands of cells. More cells mean more weight. More weight means less payload capacity. In freight, payload